Dear students, in the last class, we have studied about oxides of nitrogen like nitrous oxide, nitric oxide, nitrogen trioxide, nitrogen dioxide, and nitrogen pentoxide, their preparation, properties, uses, and structures. Today, let us study about oxyacids of nitrogen, which includes hyponitrous acid, HNO, which gets dimerized to form H2N2O2. Hypo means one oxygen less. Nitrous acid, formula HNO2, nitric acid, HNO3, per-nitric acid, HNO4, per refers to one oxygen more. Coming to the hyponitrous acid, it is prepared by treating silver hyponitrite with a solution of HCl in dry ether or with H2S. So, when a silver hyponitrite, that is Ag2N2O2, when it is treated with 2HCl gives H2N2O2 and the 2AgCl. Similarly, with H2S, it forms silver sulfide precipitate. The solution is evaporated to dryness in vacuum to get hygroscopic crystals of hyponitrous acid. It decomposes slowly when exposed to air to form nitrous acid and nitric acid. So that is H2N2O2 plus 3O2 gives rise to 2HNO2 plus 2HNO3. The aqueous solution of the acid decomposes on heating, evolving nitrous oxide. H2N2O2 on heating gives rise to nitrous oxide, that is N2O plus H2O. It is a weak dibasic acid, forms a salt of hyponitrite. Example, barium hyponitrite, formula BaN2O2. The dipole moment and spectral studies gives trans structure of hyponitrous acid. This is more stable. In all these acids, the non-metal is attached to OH groups. Coming to the nitrous acid. This is an unstable acid and is known only in solution. It is prepared by the action of water on its anhydride. That is, when the nitric oxide is treated with water, we get HNO2, that is nitrous acid. It is also prepared by the action of barium nitrite with calculated quantity of dilute sulfuric acid. Since the acid is very unstable, the reaction is carried out at the temperature of freezing mixture. Barium nitrite, when it is treated with sulfuric acid at a temperature of freezing mixture, we get barium sulfate and nitrous acid. It is an unstable weak acid, undergoes auto-oxidation in cold solution and at hot condition decomposes to nitric oxide and nitrogen dioxide. 3HNO2 undergoes auto-oxidation in cold, gives rise to 2NO2 plus 2HNO3 plus H2O. So in this case, the nitrogen oxidation state in HNO2 is plus 3 and this gets oxidized to plus 4 in case of nitrogen dioxide and then the plus 5 in case of the nitric acid. So in the hot condition, the nitrous acid gives H2O and N2O3, which further undergoes decomposition to form nitric oxide and nitrogen dioxide. It acts as a good oxidizing agent. Nitrous acid, whose oxidation state is +3, when it is treated with H2S, gives rise to H2O plus 2NO plus S. Here, the HNO2 undergoes reduction to form the nitric oxide, where the oxidation state is +2, and H2S, the sulfur oxidation state is -2. It changes to sulfur, whose oxidation state is 0. Therefore, the nitrous acid acts as an oxidizing agent. Similarly, it acts as an oxidizing agent to oxidize potassium iodide to iodine and also sulfur dioxide to sulfuric acid. It also acts as a good reducing agent. It reduces iodine, bromine, hydrogen peroxide, acidified KMnO4 and potassium dichromate solution. So the examples: HNO2 plus I2 plus H2O gives rise to 2HI plus 2HNO3. Here nitrous acid gets oxidized to nitric acid, where the oxidation number increases from +3 to +5. Iodine, whose oxidation state is 0, reduces to -1 in HI. Nitrous acid reacts with alkalis to form nitrites, which are much more stable than nitrous acid. Therefore, it is an acid-base reaction. Nitrous acid reacts with NaOH to form sodium nitrite and water. It is used in the preparation of azo dyes and also as an oxidizing and reducing agent in analytical chemistry. Coming to the structure of nitrous acid. When ethyl bromide is distilled with sodium silver nitrite, a mixture consisting of ethyl nitrite, that is C2H5ONO, and nitroethane, C2H5NO2, is formed. This shows that nitrous acid exhibits the following two tautomeric forms. So, in one structure, the nitrogen atom is linked to oxygen and also the link to the another oxygen through a coordinate bond, where the hydrogen atom is linked to the nitrogen. In another structure, it is the OH group is linked to the nitrogen and which is further linked to the oxygen through a double bond. In 1951, L.H. Jones from an infrared studies gave the following structure to the nitrous acid vapors. The solid NO2- has following structure. The structures are shown, so where the bond length is 1.46 angstrom between nitrogen and oxygen, and the bond angle is 104 degree, and also between nitrogen and oxygen of NOH group is 1.20 angstrom. Coming to the next, nitric acid, HNO3. It is prepared by heating concentrated sulfuric acid and an alkali nitrate in a glass retort. When sodium nitrate is treated with sulfuric acid, we get sodium sulfate and nitric acid. The nitric acid formed on distillation gives concentrated nitric acid, which is about 68%, which forms a constant boiling mixture. This on further distillation with concentrated sulfuric acid gives 98% nitric acid. Fuming nitric acid is prepared by distilling concentrated nitric acid with a little starch. The starch reduces some acid to nitrogen dioxide, which dissolves in the remaining acid to form fuming nitric acid. This acid is yellow in color due to the dissolved oxides of nitrogen. It is much more powerful oxidizing agent and nitrating agent than concentrated nitric acid. It is a strong oxidizing agent. So during the reaction, HNO3 turns to NO2 plus H2O plus nascent oxygen. That nascent oxygen is responsible for the oxidation. It oxidizes sulfur to the nitrogen dioxide and it oxidizes sulfur to sulfuric acid, and nitric acid reduces to nitrogen dioxide. It oxidizes phosphorus to orthophosphoric acid and reduces nitric acid to nitrogen dioxide, where the oxidation state of nitric acid changes from +5 to +4. The other reactions are with sulfur dioxide and H2S, where sulfur dioxide turns to sulfuric acid and H2S turns to sulfur. It oxidizes acidified ferrous sulfate to ferric sulfate. The nitric oxide formed gives a dark brown ring at the junction of the two liquids. Therefore, this reaction is also called brown ring test, which is used as the confirmative test to detect the nitrate radical. Action on metals. Most of the metals, with the exceptions of gold and platinum, are attacked by nitric acid. Most of the metals form nitrates with the exception of metals like tin and antimony, which forms metal oxides. During the reaction, a part of the acid is reduced to give products like nitrogen dioxide, nitric oxide, nitrous oxide, ammonia, and even hydrogen. The nature of the products depends upon the concentration of the nitric acid, temperature, and the nature of the metal. It is believed that the primary action in each case is the liberation of the nascent hydrogen, which then reduces the acid to different reaction products. When it is treated with very dilute nitric acid, it produces ammonium nitrate. Example, the zinc gives ammonium nitrate with very dilute nitric acid. The reaction is 4Zn plus 10HNO3 gives rise to 4ZnNO3 twice plus 3H2O plus NH4NO3. With dilute nitric acid, it produces hydrogen with magnesium, and it produces nitrous oxide with zinc and ammonium nitrate with tin and nitric oxide with copper. The reactions are Mg plus 2HNO3 gives rise to MgNO3 twice plus H2. 4Zn plus 10HNO3 gives rise to 4ZnNO3 twice plus 5H2O plus N2O. 4Sn plus 10HNO3 gives rise to 4SnNO3 twice, that is stannous nitrate, plus 3H2O plus NH4NO3. 3Cu plus 8HNO3 gives rise to 3CuNO3 twice plus 4H2O plus 2NO. All these reactions are very important reactions. With concentrated nitric acid, nitrogen dioxide is produced. The example, the copper with concentrated nitric acid gives rise to nitrogen dioxide. Similar reactions you come across even with tin and the zinc. Cu plus 4HNO3 gives rise to CuNO3 twice plus 2H2O plus 2NO2, and similarly you get the NO2 with other metals also. Next we study aquaregia. Aquaregia is a mixture of one part of HNO3 and 3 parts of HCl. During the reaction, nascent chlorine is produced, which dissolves gold and platinum. So, HNO3 plus 3HCl gives rise to NOCl called nitrosyl chloride, 2H2O and 2 nascent chlorine atoms. So gold reacts with HNO3 and HCl, that is aquaresia, and forms gold chloride, 2H2O, and nitric oxide is produced. Similarly, the reaction takes place with platinum, which gives platinum tetrachloride, nitric oxide, and water. Next, we take another nitrating property. Concentrated nitric acid reacts with organic compounds and forms their nitro compounds. The reaction takes place in the presence of stronger acids like concentrated sulfuric acid to produce nitronium ion, which replaces the hydrogen ions of an organic compound to form nitro derivatives. Benzene reacts with nitric acid in presence of sulfuric acid to form nitrobenzene and water. Nitric acid decomposes metallic oxides, carbonates, sulfides, and hydroxides to respective nitrates. CuO plus 2HNO3 gives rise to CuNO3 twice plus H2O, where copper oxide turns to copper nitrate. Similarly, sodium carbonate turns to sodium nitrate and carbon dioxide. Sodium sulfide turns to sodium nitrate and hydrogen sulfide. This further, the hydrogen sulfide turns to sulfur. Sodium sulfite reacts with nitric acid to form sodium nitrate and sulfur dioxide is produced. This the sodium produced. It also reacts with potassium hydroxide to form potassium nitrate with nitric acid. Nitric acid is used in the manufacture of nitrates, which further used as fertilizers. Silver nitrate is used in photography. Sodium nitrate is used in the manufacture of gunpowder and fireworks. Nitric acid is used in the manufacture of explosives like nitroglycerin, dynamite, trinitrotoluene, picric acid, etc. It is also used in the manufacture of artificial silk, dyes, medicines, and perfumes. It is used in the purification of gold and silver and also the manufacture of sulfuric acid. Coming to the structure of nitric acid, which contains one OH group and attached to the nitrogen atom, and this nitrogen atom is attached to oxygen through double bond and another oxygen through a coordinate bond. The HON bond angle is 102 degree and ONO bond angle is 112 degree. And the ONO double bond angle is 116 degree and OH bond distance is 0.96 angstrom. The nitrogen and oxygen, where the oxygen is linked to the hydrogen, that's OH group, this bond distance is 1.41 angstrom. N double bond O bond distance is 1.22 angstroms. And the nitrogen atom, here it is sp2 hybridized and it has trigonal planar geometry. Coming to the next acid called the pernitric acid, formula HNO4. It is prepared by dissolving nitrogen pentoxide in anhydrous hydrogen peroxide. The N2O5 reacts with hydrogen peroxide to form HNO4 and HNO3. It is unstable and explosive. It smells like bleaching powder. It is powerful oxidizing agent. The structure of HNO4 is where we have the peroxy linkage between the nitrogen and the OH group. And this nitrogen is linked to the oxygen through double bond and also through a coordinate bond. Now coming to the structures of oxyacids of nitrogen. As I have said, hyponitrous acid, then we have nitrous acid, we have the nitric acid and also pernitric acid. Apart from this, we also have hydronitrous acid and pernitrous acid also. The structures are shown. As you know, in all these cases, nitrogen is linked to the OH groups. Students, if OH group is attached to the non-metal, it results acids. If OH is linked to the metal, it results the hydroxides, that is the bases. In all these the cases, you have the OH group where H can be replaced very easily. Therefore, these forms acids. Hyponitrous acid contains N double bond N group and both the nitrogen atoms contains the OH groups. In case of hydronitrous acid, so where the N single bond N and both the nitrogen contains the 2,2 OH groups. So therefore the formula becomes H4N2O4. Coming to the nitrous acid is HNO2 where the nitrogen is linked to the oxygen through a double bond and it is also linked to another OH group. And then we also have the another, that is pernitrous acid. Per means one oxygen more. In this case, the nitrogen atom is linked to the oxygen through double bond and another through OO group, that is peroxy group, and the formula becomes HNO3. But the structure is pernitrous acid. It is not nitric acid. Coming to the nitric acid, its also formula is HNO3 where the structure is nitrogen is linked to oxygen through a double bond O and it is linked to the OH group and it is also linked to the another oxygen through a coordinate bond where the nitrogen gets positive charge and oxygen gets negative charge. In case of the pernitric acid, so we have once again the peroxy group. This slide shows these various the oxyacids of nitrogen and their methods of preparation. Here, this slide shows the structures of the nitrous acid and nitric acid and their bond distances are also mentioned. In case of the nitric acid, so the bond distances and bond angles are mentioned here and which is also already explained. In case of nitrous acid also, the bond angles and bond distances are mentioned. Nitric acid is a strong oxidizing agent. It is used in fertilizer and explosive production. It is very important industrial compound. Nitrous acid is less stable, weak acid, tends to disclose disproportionate to nitric oxide and nitric acid. Students, go through these aspects and try to learn about the oxyacids of nitrogen. Thank you.